So thank you very much to everybody for hosting this presentation today. For us, as a small regional geological survey, is a great honor and a great pleasure to show you our experience with the PS-InSAR monitoring system. So I will begin with just some information about our very small region and our survey and the way in which are our tasks. And from the first slide, you can understand that we are an operational geological survey that is in charge mainly to work with landslides in order to monitor them, to detect them, to assess to the risk assessment still related to landslides, and in the end, in many cases, to perform remediation works. So I can show you how our system can integrate in our practice, more or less now in our everyday practice. So natural hazards in Aosta Valley are many kinds. As I said earlier, we will focus mainly on landslide hazard and its monitoring. Okay, as you can see in this slide, we are the smallest Italian region. Is a square 80 kilometers per 40 kilometers wide, and but we have some feature very important for the geologists. We are the Italian region with the higher susceptibility for landslide phenomena, and together with the important communication way with Switzerland and France. We are cornered within between Switzerland and France in the Northwestern Italy. Our monitoring network follows continuously H24 6 great landslides that are their activation is likely to trigger civil protection plan, so they are placed under early warning systems, and we follow this continuously other 10 more or less important landslides that can still belong in the future to the club of the 6 landslides more important. Okay, and here you can have a look to which is the importance of the communication axis for our region. These are the data that are provided by the European Union about the goods and freight traffic between the main region and across the Mont Blanc Tunnel and its closure. Due to the Great Fire of 1999, it was closed for 3 years, about 3 years, and it induced a damage to the Italian economy of about 2 million euros each day of closure. The other tunnel is the Grand Saint Bernard tunnel that has a more regional importance. Well, just 2 generalities about the civil protection in Valle d'Aosta and in Italy. Civil protection regulatory framework in Valle d'Aosta is more or less the same of the other regions, because it makes sense because regions always or often have to work in a joint way, so we have the same regulations. But as you can see from this landslide, so from this slide, the landslides and the natural hazards, mostly the hydrogeological hazards, play the main role in the civil protection activities. And so the involvement of the regional surveys, regional geological surveys, is very important in the first two of the phases, of the civil protection activities, that are forecasting and prevention, and also in a bit slightly in emergency and emergency overcoming. So InSAR satellite monitoring enables the civil protection to have a very useful tool, especially in the phases of forecasting and prevention. So we had a look to it to take advantage of this new technology to improve the quality and the intensity of our activity. I will show you after later in which is the way. So the geological survey are, for the Italian regulation framework, are one of the support functions of the civil protection system that are integrating forecasting, prevention, rescue, as I said earlier, and they provide technical insights, technical forecasting, and technical activity to build the event scenarios for the civil protection authority, and during the emergency to assess which is the evolution in terms of forecasting, but also in terms of damage assessment when the event is over or is ending. Okay, and our new regional scale integrated monitoring system allowed us to move from a reactive approach to a more proactive approach. What you see at the top of the slide are the traditional techniques from starting from direct surveying down to the most sophisticated monitoring systems, but in the end we usually react to known hazards more or less late. Okay, now with the integration of the satellite PS-InSAR system, you see also the optical systems, we can adopt a more proactive approach. And how? So, you know, the new architecture, since we are a public service, our mission is to implement all the technical specialist activities to study and monitoring of landslides for the activation of the risk reduction actions and for the management of the landslide monitoring networks for civil protection. So the great question that we had before have the availability of the PS-InSAR monitoring was why intensively monitor some unstable areas and not others? And are we sure that all unstable slopes on our territory are being known or controlled? Okay, the risk is that some potentially dangerous areas are being ignored, while other areas are too intensively monitored, causing a waste of resources, even financial resources. So we also need objective and rational criteria to prioritize our on-site monitoring activities. And so far, we had only static tools like the landslide inventories that gave you an idea about the susceptibility. But they are static tools, and their elaboration needs a great amount of works in the field and the interpretation of aerial photos and so on. So the advent of the satellite radar interferometry may help to improve our regional scale landslide management program. Okay, and how to do that? So we followed one of the many ways that are available, and we choose this one. The goal was the method was made on our previous experience with the integration of the monitoring systems. Integration of different monitoring systems is a quite common practice in geohazard monitoring. So we moved toward an upscaling of this concept. We perform integration at a site scale nearly daily because we have, for instance, as you can see from the slide, to get from punctual data, we have to spatialize them, integrating, for instance, a robotized total station with a PSInSAR monitoring system. So we perform scaling integration with satellite. Okay, the reason why we implemented this kind of integration can be explained from looking at the next two slides. This is the first one. In this table, you can see a comparison between the satellite INSAR monitoring system and the most special effective ground-based monitoring tool that is the ground-based INSAR, which can monitor a front of about 1 kilometer mass. So the bottom line of this table is that INSAR can fill a gap that any other instrument can bridge today, and probably in the next years, during the next years. But when it comes to the use of satellite monitoring for the emergency monitoring, as you can see, it is not suitable and must be replaced by other instruments. Nevertheless, the regional scale monitoring system can be effective only when satellite monitoring is integrated with other monitoring systems, and vice versa too. So the result, as you can see from this slide, is that shows you the location of our 6 main landslides under early warning systems. These are the red squares, and the discontinuously monitored systems are the blue squares. We can start from this picture, a very punctual and discontinuous system, to this one. And even though we are in a very in a very morphologically complicated mountain region, we have the highest peak in the Alps, that is the Mont Blanc, for near 4,800 meters high. And we have a lot of shadow areas. We have 3% of our region covered by glaciers and forests. Even though we have all these features that hamper a full coverage by PS-InSAR, we can, in the end, obtain a good coverage by the satellite and extend our monitor. So this integration made us able to structure our monitoring network on 3 levels, each one corresponding to an increasing level of criticality. Okay, what we are performing now? After 2 years of pandemic, probably this concept of screening has become more popular in good and in a good and in a not good sense. But as you can see, the investigation, the EO monitoring by PS-InSAR allows us to, in a quite common sense procedure, to investigate the new phenomena that we are detecting, potential phenomena that of ground deformation that we are detecting by PS-InSAR. Okay. Okay, we organized, as I said earlier, our regional network on 3 levels. You can see, you can watch in this slide the requirements of each network. It is also being published. And okay, these 3 kind of networks, and mainly the satellite, may support the prevention in the first case by land management, the prevention also by remediation works when it's integrated with the other more geotechnical instruments. And in this case, the satellite is useless, and we have to act for early warning with direct on-site instruments. Okay, and until now, sorry, so far you saw what we can do with a very intensive monitoring provided by Sentinel-1 with a revisitation time of nearly 15 days and with the maps provided by it. But moving forward, we can also exploit this data for monitoring and for maybe forecast and prevention. And so we adopted a procedure based on the concept of displacement anomaly that has been elaborated by the University of Florence, that is also a partner in the ASTOOL project. And we have cooperated with Florence University for a long time to develop our PS-InSAR monitoring system. So we had a very good feedback from the activity. As you can see, when we have a deformation, each acceleration detected in compared to the last 150 days is highlighted as an anomaly, an anomalous PS point, and it is dispatched as an alert, as an alarm, sorry, to our regional monitoring system center. Sorry. Okay. As a screening tool, it is quick, very fast, very cost-effective. PS-InSAR monitoring by anomalies, I intend, is very cost-effective. But on the other hand, it produces a lot of false positive. Okay? So, like in COVID-19, the same thing. So, further investigation in case of a positive test are required. And the positive case in our situation is the signalation of the anomaly. So, we are starting a remote validation in order to assess if, for instance, the anomaly is due to snow cover. That is a quite common phenomenon that occurs, and then that creates some false positive. And we are integrating it with other maps or that we have, like the geological map, inventory, national landslide inventory, the regional inventory of slope instabilities, just to assess if the anomaly is already placed on a susceptible zone. Okay. This is performed by the workflow that is a semi-automatic workflow that runs under QGIS, so is an open source workflow, and it has also some manual phase of assessment, and we can filter the anomalies in order to focus our activity only on the points, on the anomalous points that are worth a field investigation. Okay? in the operative validation, we sorry, I come back just 2 slides. As you can see, the automatic procedure produces 3 level crosses, makes a correlation within the dangerosity and the risk, the upper risk crossing the maps with the maps of the targets, and generates an empirical heuristical score that in the end can produce 3 kinds of priority: green, yellow, and red. Low risk requires a low priority, so we wait for the next release of the PS-InSAR anomaly map. Medium risk requires a field investigation within 15 days, and high risk requires a field investigation within 7 days. And during these activities, we evaluate all the features that we can find in the field, and in case of a suspect situation, we can perform further investigations and place eventually in the end the site in the level 2 network, or is the case is worse and more evolutionary, under the level 3, and so therefore under an early warning system. And until now, so far, this hopefully that it's not happened. Okay. So in the end, I'm going to conclude to end my presentation. All this kind of investigation generated by the satellite monitoring has to be recorded in a web-based tool, just to provide evidence for the future investigation that could happen again. And we generate under the web application, we generate a more or less what you could call a monographic form, okay? And to keep the record of what type of actions has been taken, because once you have a monitoring system available, you are also responsible both technically but also legally for this kind of for the results that you get from the monitoring network. When you are going in the field, you can acquire more evidences of deformation, like cracks, classical cracks in man-made artifacts and so on. And okay, the last 2 slides are about other benefits of the satellite monitoring integration. When the ground deformation is affecting infrastructures with rates that are slow, like in this case is a road with a V deformation that is not very high, you can, with the satellite monitoring, you can reduce the density of on-site instrumentation, and you can also delay the structural remediation work in order to make a better project and not act in an emergency situation. And so you can, how to say, to optimize the allocation of your financial results. And this is, in my opinion, another great benefit that has not to be underestimated in this case. So, just something to end my presentation is short synthesis. So, our experience is that we are implementing a Landslide hazard screening tool, and as any screening tool, as I said earlier, like in medicine, it is low cost, produces a lot of false positive, so it needs a filtering procedure. Some slots are not covered, so you have, in that places, you have to perform traditional monitoring. But on the other hand, you can focus and concentrate on in that places your more expensive resources, economical and human resources that you need to perform traditional monitoring compared with satellite monitoring. And the phenomena with the evolution faster than 800 millimeters per year are not being monitored. So rockfalls and other kind of very fast landslide can't be monitored, but by the PS-InSAR monitoring, at least with the actual tools. So, on the other hand, we have you have to perform a good interpretation and an effective interpretation. You have to know very deeply the site and the regional geology for ground calibration, and you have to need a platform or a system to gather all the data like optical satellite inventory subsurface in order to speed your evaluation after you get the anomaly alert. And it's good for rock deformation assessment and in general for embankments and so on. For bridges, buildings, dams, it's promising, but still under evaluation. And case by case, it has been to be evaluated. So thank you again for your attention. And now I'm available for all the questions and doubt that you can have. Thank you.
Thank you very much, Davide. So we are waiting for the questions now, if there are any.